Okay, so now let's prove this property formally for any relation, any equivalence relation. So theorem, let R be an equivalence relation on a set A then the following statements are equivalent. So the first one, A is in relation with B. Second one, the class of A, equivalence class of A is equal to equivalence class of B. And the third condition, the intersection of equivalence class of A and equivalence class of B is not equal to the empty set. So for an equivalence relation, when you consider two equivalence classes, either they are equal, or if they are not equal, their intersection will be empty set. Similar to what we saw here, see? Two distinct equivalence classes, their intersection is empty. So here we are saying it in this format that we are saying that two equivalence classes are equal if and only if their intersection is non-empty. You could also say this as in the form that, two equivalence classes are different if and only if their intersection is empty set. You could also say it that way. Okay, so let's see how we can prove this proof. And so we want to prove 1 implies 2 and 2 implies 3 and 3 implies 1. So to prove 1 implies 2, so we want to show if A is in relation with B, then equivalence of A is equal to equivalence class of B. So suppose that A and B is in R, and we want to show, so we want to show that equivalence class of A is equal to equivalence class of B. But how can we show that? To show equivalence class of A is equal to equivalence class of B, what we have to show is that, we have to show equivalence class of A is a subset of equivalence class of B, and equivalence class of B is a subset of equivalence class of A. So we want to show equivalence class of A is a subset of equivalence class of B, and equivalence class of B is a subset of equivalence class of A. So for the first one, let me take X in the equivalence class of A. Then what can we say? Then we can say that X and A is in R, right? So when you take an element in the equivalence class of A, what elements do we have here in the equivalence class of A? All the elements X, which are in a relation with A, meaning that either X and A is in R, or A and X is in R. So in this case, I wrote, X and A is in R, and both of them will be in R, because remember, equivalence relation is symmetric. So if X and A is in R, A and X will be also in R. But I want to use this one. I want to use the fact that X and A is in R. What else do we know? Why do I want to use this one? Because I also know that A and B is in R. We also know A and B is in R. So these two together implies that X and B is in R, right? If X and A is in R and A and B is in R, then that means X and B is in R. And that means X belongs to equivalence class of B, right? If X and B is in R, then that means X is in equivalence class of B. Because again, equivalence class of B means all elements X which are in relation with B. Okay, so we showed that if X is in equivalence class of A, then X will be in equivalence class of B. So thus, equivalence class of A is a subset of equivalence class of B. Similarly, if you take, let's say, some X in equivalence class of B, then we can say that X and B X and, or let me say, yeah, B and X. Let me say B and X will be in R, right? And we were assuming that A and B is also in R. So A and B is in R, and B and X is in R. So these two together mean A and X is in R. A and X in R means that X belongs to equivalence class of A. So we can conclude that equivalence class of B is a subset of equivalence class of A. So these two together mean, equivalence class of A is equal to equivalence class of B. And we are done for this part, because if equivalence class of A is a subset of equivalence class of B and equivalence class of B is a subset of equivalence class of A, then those two equivalent classes must be equal. Okay, so now let's prove 2 to 3. 2 to 3, how can we prove? Next, to prove 2 to 3. 2 to 3, so we are assuming that equivalence class of A and equivalence class of B. I want to show that their intersection is non-empty. Okay, so how can I prove that the intersection is non-empty? Well, this is very easy to prove, because what will be the intersection of equivalence class of A and B? I want to show that that is non-empty, right? So what will be the intersection of these two, equivalence class of A and B? What is the intersection going to be? So equivalence class of A intersection equivalence class of B. So this will be equal to equivalence class of A intersection equivalence class of A itself. Right? This is my assumption. I'm assuming that 2 holds. So if 2 holds, that means equivalence class of A is equal to equivalence class of B. And therefore, equivalence class of A intersection equivalence class of B will be equivalence class of A intersection itself. And instead, the intersection itself is equivalence class of A. And this is, of course, not empty, since A belongs to equivalence class of A. So a set intersection itself is, of course, itself, and that intersection equivalence class of A is non-empty set. Why? Because at least A is there. At least I can say that A is in relation with itself, right? Because equivalence class of A means all the elements which are in relation with A. Well, A is in relation with itself. Why? Because the relation is reflexive. Remember, I'm assuming that the relation is equivalence relation, so it's reflexive, and therefore A is in relation with itself. And well, if this equivalence class at least contains A, therefore it will be non-empty. Okay, now, so this is 2 to 3. Next, to prove 3 implies 1. So suppose that equivalence class of A intersection equivalence class of B is non-empty. And we want to show A and B is in R, right? I want to show 3 to 1. 3 to 1, what is 1? 1 is A, R, B, or A and B is in R. So I'm assuming that the intersection A and B equivalence classes are non-empty. I want to show that A and B is in R. So if the intersection is non-empty, that means it contains at least one element, right? So since equivalence class of A intersection equivalence class of B is non-empty, we can conclude that there exists X in the intersection, some element X in the intersection. Now, well, X belongs to equivalence class of A, so that means A and X is in R. Similarly, X is in equivalence class of B, so that means X and B is in R. So see, A and X is in R. X and B is also in R. So, and R is transitive, right? See, A and X is in R, X and B in R, and R is transitive because it's equivalence relation. So I can conclude that A and B is in R because R is an equivalence relation and therefore transitive. Well, that's it. We wanted to show that A and B is in R. We showed that A and B is in R. So the only thing we had to use the fact that the intersection of these equivalence classes are non-empty. So we took an element X there in the intersection. Well, X being in the equivalence class of A means A and X is in R. Well, remember X in the equivalence class of A means A and X and A both will be in R. But here I will just use the fact that A and X is in R. I don't need the other part. Similarly, if X is in B, equivalence class of B, that means X and B and X, both of them will be in R. But again, this time I will just use the fact that X and B is in R. Now, if A and X in R and X and B in R, then I can conclude A and B must be in R. So A and B in R, and yeah, that's what we wanted to show. So we proved 3 to 1 as well. So the proof is complete now. We showed 1 implies 2, 2 implies 3, and 3 implies 1. So that means the conditions 1, 2, and 3 are equivalent. So one remark is that since 2 and 3 above are equivalent, we can conclude that two equivalence classes. So I can conclude that equivalence class of A is different than equivalence class of B if and only if the intersection of them is the empty set. So one way was, we could say that equivalence class of A equals equivalence class of B if and only if the intersection is non-empty. We could also say this as equivalence class of A is different than equivalence class of B if and only if their intersection is empty set. So this is another way to talk about this equivalency of these two conditions, 2 and 3. Okay. So for example, in example above, equivalence class of 1 is not same as equivalence class of 2, and equivalence class of 1 intersection equivalence class of 2 as the empty set. So this example here I'm referring equivalence class of 1 and 2 were different and their intersection is empty set, which is something we expect to happen from the theorem or from the remark after the theorem. Okay, so now I want to talk about partition of a set. So let S be a set. We say that the collection A1, A2, A3, and the collection these of subsets of S is a partition for S. Is a partition for S if AI intersection AJ is empty set for I not equal to J, and the union of all of them is equal to S. So if you have a collection of subsets of a set which are pairwise disjoint, so any two of them that you consider, they have empty intersection. See? Here in this picture, if I consider any two sets like A1 and A2, no intersection, A1, A3, no intersection, A1, A4, no intersection, and so on, or A2, A3, A2, A4. So these sets are pairwise disjoint. Any two of them have empty intersection, and the union of all of them is the whole set S. Then we say that these sets, these collections of subsets of S is a partition for S. So in this case, A1 to A5 is a partition for S because they're pairwise disjoint and the union of all of them is S. Okay, so let's look at an example. Let's look at a simple example first. Let S equals, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And let's say A1 equals 1, 3, 4, 5. A2 equals 2, 6, 7. And A3 equals 8, 9, 10. Then A1 intersection A2 is same as A1 intersection A3, same as A2 intersection A3, and all of these are empty set. And we also have the union of all of them, A1 union A2 union A3 equals S. Thus, A1, A2, A3 is a partition for S. Right? See, A1 and A2, we have a set S with 10 elements. A1 has 4 elements, A2 3 elements, A3 3 elements, and union of all of them is the whole S. And any two of them have empty intersection, A1 with A2, A2 empty intersection, A1 with A3 empty intersection, A2 with A3 also empty intersection. Okay, so if the sets are pairwise disjoint, meaning that in the intersection of any of two of them is empty set and the whole union is S, then we call that collection a partition for S. Okay, now why am I mentioning this concept? Because when we have an equivalence relation and therefore we have equivalence classes, the set of all equivalence classes will be a partition for our set A. So let me mention this as a theorem. let R be an equivalence relation on a set A, then the set of all distinct the set of all equivalence classes forms a partition for A. The set of all equivalence classes will be a partition for A. Okay, now if you want to prove this, so the collection that we are talking about, so we want to show that this collection of equivalence classes where A belongs to R is an equivalence, is a partition for A. So first, a union of all these equivalence classes will be the whole set A. So that's the first thing. So the union of all of them is the whole set Y. So because, if X note, if let's say some X is in A, then we can say that X and X is in R. So X belongs to, because R is reflexive, right? R is reflexive, so X and X is in R. So we can say X belongs to the equivalence class of X itself. So that means X belongs to the union of all equivalence classes. So every element in A that you consider, I want to show that is in one of the equivalence classes. In X will be in which one of the equivalence classes? X is in relation with itself because R is equivalence relation, therefore it's reflexive, and therefore X is in the equivalence class of X. So X is in one of the equivalence classes and therefore is in the union of all of them as well. And the second condition that we need to show is that we have to show that the intersection of any two distinct one is empty set. Because remember, for the partition, for a collection of set to be a partition, I need to show the union of all of them is the whole set. And also, any two of them have empty intersection. So let A and B, equivalence class of A and equivalence class of B, be two distinct equivalence classes i.e. equivalence class of A is different than equivalence class of B. Then what can we say? Then we can say that equivalence class of A intersection with equivalence class of B is equal to empty set. So let me call this remark that we mentioned this there. Yeah, we already mentioned this as a remark here. So let me call this one remark star. So C remark C remark star above. Okay, in the remark we exactly said this, that if two equivalence classes are different, then their intersection is empty set. So these two together, 1 and 2 imply that the set of equivalence classes forms a partition forms a partition for the set A. Okay, so that's one thing. So let's look at an example. So one example we saw, that let's say congruence mod 2. So then we have two equivalent classes, two distinct. We saw that we have two distinct equivalence classes. Namely, equivalence class of 1 and equivalence class of 2. And these form a partition for Z. Equivalence class of 1 union equivalence class of 2 is the whole Z, and these two have no intersection. Equivalence class of 1 intersection equivalence class of 2 is equal to the empty set. Okay. So you could think about think of this theorem in other contexts as well for other examples. So for example, let's say what else did we consider as equivalence relation? Okay, maybe I can leave this one as exercise, that for A equals, let's say, set of all real numbers, and the relation R defined as ARB if absolute value A equals absolute value B. Verify verify that the set of all equivalence classes forms a partition for R. Okay, so we can verify that for this relation, the set of all equivalence classes forms a partition for R. So you need to show that the union of all of them is the all real numbers, and the intersection of any two of them, any two distinct equivalence classes, is the empty set. So we know this happens, but you want to verify it because we already showed that this relation is an equivalence relation. So we expect this property to hold. Okay, so now another concept we want to look at, so defining an equivalence relation given a partition for a set A. See, what have we done so far in the previous topics? So in above, we saw that given a partition, given an equivalence relation R on a set A, the set of all equivalence classes forms a partition for A. Now we want to look at the converse. Now conversely, if a partition for a set A is given, say, for example, A1, A2, and so on, then we can, given this, we can define an equivalence relation R on A as follows. The equivalence relation we want to define is that we want to say that X is in relation with Y. Okay, previously we had the relation, we found the partition given the relation. Now it's the opposite. Let's say we have the partition and we want to define the relation using the partition. Okay, it's the other way around. So how do we want to define the relation? We want to say that X is in relation with Y if there exists some index I such that X and Y belong to, both of them belong to, let's say, AI. So if both X and Y are in one of the AIs, then we can say X is in relation with Y. So this is the way we are defining the relation this way, and our claim is that this relation defined this way is an equivalence relation on A. So now we need to prove this. So proof of R being an equivalence relation. So first we have to prove reflexive. So given A in A, right? So we can say that there exists some I such that A is in AI, right? Since A1, A2, and so on is a partition for A. See, remember, we are assuming that we have a partition for A. And the partition is like A1, A2, and so on. The capital A1, capital A2, and so on. So because we have partition, the union of all AIs, capital A1, A2, and so on, the union is whole S or whole A here. So if I have some element A in A, it has to be in one of them because the union of A1, A2, and so on is the whole A. So small a has to be in at least one of the AIs. So then that means that A are A, since A and A, both of them are in AI. Remember, when do we say that two elements are in relation with each other? Two elements are in relation with each other if there exists some index I that both X and Y are in AI. Well, here, both A and A, which means just A, is in AI, so A is in relation with itself. So second property, symmetric. So suppose that let's say X is in relation with Y, then what can we say? Then we can say there exists some index I such that X and Y, they're both in AI, right? Well, the same reasoning means that Y and X are also in the relation for, yeah, X and Y both in AI for some I, therefore Y is also in relation with X. All right, X and Y both are in AI. So, and X is in relation with Y. So Y is also in relation with X because of the same reasoning. Because when can I say Y is in relation with X? If Y and X are both in AI. Well, I just assume that X and Y both in AI. Therefore, of course, Y and X also both in AI. So we show that if X is in relation with Y, then Y is in relation with X, which implies the symmetric. And the third one, transitive. So suppose that X is in relation with Y and Y is in relation with Z. Then what can we say? Then we can say that there exists some I such that X and Y in AI. Also, we can say there exists some J such that Y and Z in AJ. Well, these two together means I must be equal to J. Can you tell me why? Why can I say that I must be equal to J if X and Y are in AI, Y and Z are in AJ? Then my claim is I must be equal to J. Otherwise, if I is not equal to J, then we can say that Y, then Y, the element Y will be in the intersection of AI and AJ, right? See, Y is in AI, Y is also in AJ. So Y is in intersection AI and AJ. And if I is not equal to J, that will be impossible and a contradiction because I am supposed to have AI intersection AJ equals empty set for I not equal to J. So this implies that AI equals AJ not equal to empty for I not equal to J. And this is contradiction with AI intersection AJ must be equal to empty set, again, for I not equal to J, according to definition of a partition. Okay, so therefore we showed that thus I must be equal to J. Now what did I have? Remember we had X and Y in AI, and Y and Z were in AJ, but I proved that I is equal to J. So that means Y and Z also in AI. Y and Z also in AI. Well, this means that these two together mean X and Z in AI. And therefore we can say that X is in relation with Z. Right? Because again, remember, when can I say that two elements are in relation? If there exists at least one index that both those elements are in AI for some index I. But here X and Z both in AI, so X is in relation with Z. Okay, so X relation with Y, and Y, we prove that if X is in relation with Y, Y in relation with Z, then we have X in relation with Z. So thus, we can say that R is transitive. So we can conclude that R is reflexive and symmetric and transitive. So that means R is an equivalence relation. Equivalence relation. Okay, so that's all we need to show, that if we have if you have a partition on a set, then we can define an equivalence relation on that set. So let's look at an example. Let A equals 1, 2, 3, 4, 5, 6. Let's say A1 equals 1, 2. A2 equals 3, 4, 5, 6. A partition, so note A1 and A2 is a partition For A, find the corresponding relation R on A. Okay, so we know that every partition corresponds to an equivalence relation, corresponding equivalence relation R on A. How did we define this type of equivalence relation? We know, or we saw above, that X is in relation with Y if what happens? If there exists some index I such that X and Y both in AI. So here, A1 is 1 and 2. So let's look at the elements of R. So for example, 1 and 1 must be in R because the 1 and 1, both of them are in A1, right? So two elements are in relation with each other if both those two elements are included in one of the capital AIs. Well, 1 and 1 in this case is in A1 because 1 and 1, both of them are in A1. And similarly, 2 and 2, and 1 and 2, and 2 and 1, right? So these must be in R because 1 and 2, both of them are in A1. So 1 is in relation with 2. Similarly, 2 is in relation with 1, again, because 2 and 1 both are in A1. And what else? So these are the elements corresponding to the elements in A1. And for A2, we have 3, 4, 5, and 6. So again, 3 and 3 must be in A2, it must be in R. 4 and 4 must be in R. 5 and 5, 6 and 6. So these must be in R because 3 and 4 and 5 and 6 are in A2. So what else can we say? We can say 3 and 4 is in A2, right? 3 and 4 in A2, 4 and 3 in A2, and 3 and 5, 5 and 3, right? See 3 and 4, for example, in A2 because 3 and 4, both of them, 3 and 4 is in R because 3 and 4, both of them in A2. Remember, when can I say that a pair is in R, X and Y is in R? If X and Y, both of them are included in one of the capital AIs. Well, here, 3 and 4, both of them in capital A2. So 3 and 4 is in A2. Similarly, 4 and 3 in A2, 3 and 5, 5 and 3 in A2. What else? 3 and 6, 6 and 3, both of them in A2. 5 and 6, 6 and 5. So 3 with 4, 5, 6. 3, 4, 3, 5, 3, 6. 4 and 5. 5 and 4. 4 with 5 and 6. 4 and 6, I think I haven't mentioned yet. 4 and 6. 6 and 4. So 4 with 5 and 4 with 6. These are in the same capital AI. So 4, 5, 5, 4, 4, 6, 6, 4. And also 5 and 6, because 5 and 6 both in same capital AI. So 5 and 6, 6 and 5. So these are all in our relation R, and that's it. Okay. So this is the equivalence relation corresponding to this partition. Once you have a partition, you can define the equivalence relation. How do you know that a particular pair is in your relation or no? If both elements of the pair, both coordinates, are in the same capital AI, then we can say that that pair is in the relation. So for example, 3 and 5 is in the same, are in the same capital AI. So 3 and 5 and 5 and 3 are in R. And so on. But for example, look at here 1 and 3, for example. 1 and 3 are not in the same capital AI, and therefore they are not 3 and 1 and 3 is not in R. Or similarly, for example, 2 and 3. 2 and 3 are not in the same capital AI. One of them capital A1, one of them capital A2. So 2 and 3 is not in R. See? We don't have 2 and 3 here because 2 and 3 are in different capital AIs. 2 is in capital A1 and 3 is in capital A2. But the rest, for example, like I said, 3 and 4 both in capital A2, therefore we have 3 and 4 and 4 and 3. Or 3 and 5 both in capital A2, so therefore we have 3 and 5 and 5 and 3, and so on. Okay, and you can check that this is an equivalence relation, meaning that it's reflexive. Obviously, it's reflexive. Every A and A is in R, and also symmetric. You can check it's symmetric whenever A and B is in R, B and A is in R. It's also transitive, meaning that if A and B and C both in R, then A and C is in R. So this is an equivalence relation corresponding to this partition. Now, if I change the partition, of course, you can change the partition. If you change the partition, you will get a different equivalence relation. So here my partition has 2 sets, contains 2 sets, but you can write a partition with 3 sets, for example, A1, A2, A3. Let's say you could say A1 is 1 and 2, A2, 3 and 4, A3, 5 and 6. That's a different partition, which will lead to a different equivalence relation. Therefore, the summary is whenever you have a partition, you can define an equivalence relation this way, that a pair is in the relation if both X and Y are in the same capital AI. And also, if you have an equivalence relation, then you can write a partition for your set. What will be the partition for the set? The set of all equivalence classes. Whenever you have equivalence relation, the set of all equivalence classes will be a partition for your set. Okay, so this is the close relation between the concept of partitions and equivalence relations. Okay, so I'll upload some exercises so that you can do some practice about these equivalence relations and equivalence classes and partitions. And also in the assignment, I'll include the questions about relations as well. Basically chapter 6, what we have done so far. Or say chapter 9, what we have done so far about the relations and equivalence relations. Okay, guys, so thank you and see you next time.